Hello and welcome to the session. My name is Can Karakuş and I'm an applied scientist at AWS working on distributed deep learning. And today we're going to talk about how to use model parallelism on Amazon SageMaker to train large models consisting of billions of trainable parameters. So quick overview of what we're going to talk about today. First, we'll start with the motivation to use model parallelism and discuss some of the use cases that are relevant. Next, we'll dive into a bit more technical details on how model parallelism works and discuss some of the technical challenges that arise when we try to implement model parallelism. Next, we'll talk about the newly launched model parallel library on Amazon SageMaker and discuss some of its main features and discuss how these features address some of the technical challenges that we discussed earlier. And in the last part, we'll go hands-on and we'll discuss how to actually use the model parallelism library on Amazon SageMaker using TensorFlow and PyTorch examples. So let's start with the question then, why use model parallelism? So the motivation for this really comes from a recent trend that we're seeing in deep learning, which is the fact that the sizes of the state-of-the-art models are exponentially growing. And we see this across many different domains from computer vision to recommendations, but especially in natural language processing. When we look at a model like BERT, which was released 2 years ago with 340 million parameters, at the time it was considered a large model. But over the last 2 years, through models such as GPT-2 and T5, we've seen a constant increase, a rapid increase in the sizes of the state-of-the-art models. And today we're talking about models like GPT-3, which is almost 3 orders of magnitude larger than BERT. And what's really driving this trend is the fact that larger models have higher representational capacity, which in turn means that they generalize better and they achieve a higher prediction accuracy in downstream tasks. And we see this in domains such as natural language processing and computer vision if we look at various benchmarks. So if we look at the dominant distributed training paradigm today, we see that it's mostly data parallelism. And if you've done any sort of distributed training in the past, the odds are you've probably done some form of data parallelism, where the idea is that every GPU gets a separate replica of the model, and they get a different batch of data, they run forward and backward pass, and they compute gradients, followed by a gradient synchronization step across GPUs. Now, this way of doing distributed training actually works pretty well for small and medium-sized models. And in fact, in last year's reInvent, we showed that you can efficiently scale to thousands of GPUs under this paradigm. But as the model size starts to grow, we see that two things start to happen. First, as we grow the model size, we notice that an ever larger fraction of GPU memory is consumed by the model parameters and the optimizer state. And there is a lesser and lesser amount of GPU memory left for storing things like activations and the data samples. So this means that we can only train with a small batch size, which limits the GPU utilization and slows down training. And further note that storing the same parameters across every GPU in our system is wasteful. So we can use that memory more efficiently. And as you scale the model size even further, and certainly when you reach the range of billions of parameters, the model no longer fits in the GPU memory, and the training becomes simply infeasible. So the solution to this problem is to switch to model parallelism, where the idea is to take a model replica and split it across multiple GPUs so that multiple GPUs collectively store a single model. And by doing that, we've effectively combined the memory of all the GPUs, we've avoided replication, and effectively increased the largest model size that we can train with. And of course, once we do that, since each GPU has a different part of the model, these devices will need to communicate during forward and backward pass stages to exchange activations and gradients to be able to train. So this was a high-level overview. Let's dive into a bit more technical detail about how model parallelism actually works. First thing to notice is that model parallelism is hard, and there are several reasons for this. First, and we will go into the details shortly, but one of the main challenges is that achieving a reasonable GPU utilization is actually quite difficult in model parallelism. It turns out that as you add more GPUs to parallelize over, your average GPU utilization actually goes down, which is the opposite of what we want. Another challenge is to be able to find efficient partitions. And there are several concerns here. As we discussed, by parallelizing the model, we're introducing communication, and we want to be able to partition in a way to minimize that communication to be able to train faster. And we also want to be able to balance the computation and memory footprint across different devices. And finding the right partition given these constraints can be difficult. And of course, with any distributed training, infrastructure management becomes a problem. And more specifically for model parallelism, it turns out that you actually need to write lots of customized training code that requires deep integration with frameworks like TensorFlow and PyTorch, which requires a deep expertise in how the model architecture works and how the software frameworks work. So let's look into this GPU utilization problem that we talked about. So if we look at this animation, we notice that, so this illustrates the forward and backward passes of the computation. We see that at any given point, only one of the GPUs is doing useful work. And this is because the deep learning computation, both forward and backward passes, are inherently sequential types of computation. And what that means is that every operation actually needs its input from another operation to be able to start executing. So this is not a very parallelizable type of computation. And as a result, we run into this issue of low GPU utilization where no matter how many GPUs we put in the system, only one of them actively work at a given time. We also discussed about the difficulty of choosing a reasonable partition. So to illustrate this, I've placed an example diagram here that represents a small model where every node represents an operation in the model and the size of the node represents how expensive that operation is. So a larger node implies a more computationally expensive operation. And the arrows that go between these nodes represent the tensors that are being exchanged. And a thicker arrow means that a larger tensor is flowing between those operations. So now given this, let's explore some example partition decisions. This could be a reasonable one where we split everything in the middle. So it seems to be balancing the operations. But if we look more carefully, there are actually two thick edges crossing those partition boundaries, which means that if we actually implement this partition, we need to exchange two large tensors in both forward and backward passes at every iteration. So that's very expensive. Let's try another partition. For example, we can choose this one, where everything inside the box goes on one GPU, everything outside it goes into another. So it turns out this is a good one in terms of a communication perspective because only small edges come out of that box, but it's actually very imbalanced. So if I do this partition, most of the work will be done by one of the GPUs and the other one will be mostly staying idle. So it turns out that for this example, if I partition in this way, I both achieve a relative degree of balance between the GPUs and a small degree of communication. But note that a real model is thousands of times more complex than this. And it's not given to us in the form of a nicely drawn diagram. but it comes in the form of hundreds and sometimes thousands of lines of model code. So given that model code, it's usually very difficult to figure out exactly where to split the model to achieve a high efficiency. So now let's move on to the newly launched model parallel library on SageMaker and discuss some of its main features. So the SageMaker model parallel library features an efficient pipeline training mechanism. And as we will see shortly, this is a feature that addresses this low GPU utilization problem in model parallelism. It also features automated model partitioning, which means that you don't need to worry about how to partition the model. The model parallel library actually analyzes your model and then comes up with the right partition for you. And of course, being a part of SageMaker, it inherits all the managed aspects of SageMaker and all its features, so you don't need to worry about managing your own infrastructure. And it tightly integrates with TensorFlow and PyTorch, which means that you don't need to worry about the intrinsics of how these frameworks handle GPU allocations. And you can get started with the library with only a few lines of code change, regardless of what model you have. So the way automated partitioning works is when you integrate your model with the model parallel library, during the first step, the model parallel library actually constructs your model, looks at its graph structure, looks at where the operations are and how they're connected, looks at where your trainable weights are, looks at the size of the exchange tensors and how long each operation takes to execute, and feeds all this data into an optimized graph partitioning algorithm. What this graph partitioning algorithm does is to balance the stored weights and activations and operations across all the available GPUs while also minimizing the communication. Once it comes up with a decision, it next moves on to implementing this decision by moving the operations to their assigned devices and executing them in a pipeline manner. So speaking of pipelining, let's explore how that works. So we said that this is a mechanism to address this low GPU utilization problem in model parallelism. So the idea in pipelining is to, at every step, split the available batch into n micro batches. A micro batch is just a subset of your batch. If your batch size is 16, a micro batch could be a smaller batch of 4 within that batch. So the way pipelining works is that we feed these micro batches sequentially into the training pipeline and build out this optimized training schedule, which determines for each step which GPU will work on which micro batch at what time. And the runtime of the model parallel library specifies the schedule and orchestrates the execution across all these GPUs in such a way that maximizes the execution time of each GPU. And if we look at the pipeline version of this of our earlier animation, we see that at a given point of time, multiple GPUs can actually work in parallel, unlike before. So now let's look into how to actually use the model parallel library on SageMaker using TensorFlow and PyTorch. So we'll start with TensorFlow. First, if you're not familiar with how to launch training on SageMaker, you can use Python SDK to first create an estimator and then call a fit function using this estimator. So while creating the estimator, we feed the relevant parameters, such as the instance type we want to use, the number of instances, etc. So to get started with using model parallel library, what we need to add to this estimator is to insert this distributions argument that has 2 keys. The first is the MPI key, and this is because the model parallel library uses MPI as a communication library underneath. And we need to feed the SM distributed key, which has the model parallel specific parameters. So if we look into them more carefully, if we look into the MPI parameters, we need to feed a couple of keys. First, we need to enable MPI. Next, we need to set the number of processes per host, which will be up to the number of GPUs per instance. So for this example, we're using a P3 8x large instance, which has 4 GPUs. So that is why I've set the number of processes per host to be 4. So model parallel library maintains a one-to-one mapping between the processes and the GPUs. If you've used Horovod in the past, this is quite similar to the way Horovod works. And if you have any custom MPI options that you'd like to feed, you can feed it as a separate key in the MPI options dictionary. Next, let's look at the model parallel parameters themselves. So these will be under a key called SM distributed, followed by an inner key called model parallel. And we will first need to enable model parallel by feeding enabled equals true. And then we'll feed a range of parameters to configure our partitioning. So in this case, the parameters that we're feeding are the partitions, which is the number of partitions that we want to split our model into, the number of micro batches that we want to split our batch size into, and whether we want our algorithm, auto-partitioning algorithm, to optimize speed or memory. So you can visit our documentation of SageMaker Distributed to see a full list of available parameters and how you can customize your partitioning. Once we've done these changes on the SageMaker Python SDK, the next step is to actually modify the training script. So here I've placed an extremely simple toy script written in TensorFlow, and now we'll go step by step and see what we need to change in that script to get started with the model parallel library. The first step is that we need to import and initialize the model parallel library. This is pretty straightforward. And what this step achieves is that it launches the backend that the model parallel library needs to exchange tensors and communicate between devices. Now, once we do that, the next step is to define our distributed model. So by defining the distributed model, we're telling the model parallel library which model we want to be partitioned. So any operation that is defined within a distributed model will be subject to partition, which is to say that only one of the GPUs will execute those operations that are inside. So to do that in TensorFlow, all I need to do is to use the Keras subclassing API, and instead of inheriting my model from Keras model class, I will inherit it from SMP, which stands for SageMaker Model Parallel, .distributed model class. And everything else remains the same. The way I define my operations, my layers, my model definition remains exactly the same. I'm just inheriting my model from the distributed model class. And now I'd like to focus on this training loop we have here. If we look carefully, there are a few standard steps there. First, there's the forward pass, which is the model call, followed by loss computation, followed by the back propagation, which is the gradient computation, get gradients call here, followed by the application of the gradients. So what I'm going to do is I will take those first 3 lines, which is the forward pass, loss computation, and the backward pass, and I'm going to extract that into a separate function. And I will decorate that function with our decorator smp.step, and then I will return whatever tensors that I will need afterwards, I will return from this function. So in this case, these are gradients and loss. So when I do this, what happens is first I've described which operations that I want to be pipelined. So in this case, we want both the forward pass and backward pass computation to be pipelined, as we discussed earlier. So that is why I'm placing those operations inside an SMP step decorator. So when this SMP step function is first executed during the first training step, what is going to happen is the input arguments in this case images and labeled tensors, will be split across their batch dimension into micro batches, and they will be fed into this SMP step function sequentially, and this whole function will be executed in a pipelined manner for each micro batch separately. And during the first step, the auto partitioning algorithm actually takes place. So before the first forward pass, the library actually first analyzes the model, does the partitioning, and then only after that starts the first step. And notice that we said that this function gets executed once per microbatch. So whatever tensors we compute inside is actually computed once per microbatch. So once we return gradients, the gradient is actually a number of different tensors once per microbatch. And the true gradient is the average of these gradients across all microbatches. So that is why once we return these gradients, we need to call reduce mean method on them to get the averaged version of gradients to be used. We also offer a manual partitioning API in case you want to customize the way you want to split your model. So to use this, all you need to do is to use the context managers, SMP.partition context managers provided by the Model Parallel API. And any operation that is placed inside such a context will be placed on the corresponding partition. And anything that is not inside in any of these contexts will be placed on the default partition, which is specified while launching the training job through the Python SDK. And to be able to use this, we also need to set auto partition to false while launching the training job. It is also possible to combine model parallelism with data parallelism. So for TensorFlow, we combine model parallelism with Horovod. So Horovod is supported. So to be able to use it with Horovod, all you need to do is to set Horovod equals to true while launching your training job, and then use the Horovod or reduce call whenever you need to average your gradients across the devices. Let's move on to PyTorch and see how that one works. So launching the training job is identical. Instead of creating a TensorFlow estimator, we create a PyTorch estimator, and all the MPI and SageMaker distributed parameters remain the same. So I'll skip over to how to modify a PyTorch training script. So once again, I've created an extremely simple toy training script here on PyTorch. And again, we'll go step by step to see what we need to change. Once again, we first need to import and initialize the model parallel library to launch our backend. Next, we actually need to wrap our model and optimizer with distributed model and distributed optimizer wrappers respectively. So as in the case of TensorFlow, what this does is to define which modules we want to be partitioned. So in the case of PyTorch, the partitioning actually occurs in the basis of modules. So each module gets assigned to a different device. So the distributed model wrapper defines the scope over which we want to do this model partitioning. And the distributed optimizer wrapper makes sure that the distributed checkpointing of the optimizer state works properly. We said that we maintain a one-to-one mapping between the CPU processes and the GPUs in the system. So to make sure that each process works with only one GPU and not interfere with the other GPUs, we actually need to make this torch CUDA set device call to make sure that every process gets one GPU. And next, once again, we'll look into the training loop, and we notice that the steps there are going in parallel with TensorFlow. First, we have the forward pass, the model call, followed by the loss computation, followed by the backward call, followed by the optimizer state. So now what I'm going to do is to extract those three middle lines, which is the forward pass, loss computation, and the backward pass. And I'll extract that into a separate function, as seen in here. And now once again, I will decorate that with smp.step. And once again, when I do that, during the first step, a model tracing step first occurs, which analyzes the model and sizes of the tensors, module execution times, etc., and feeds that to our partitioning algorithm, which does the module assignment and moving of parameters, followed by the pipelined execution. So one key thing to notice here, which is different from TensorFlow, is that we also need to change how we're calling the backward function. So here, instead of calling loss.backward, as is usually done in PyTorch API, we're calling model.backward and pass the loss tensor as an argument to that. This allows the model parallel runtime to take control of the backward pass so that we can actually pipeline the computation. And once we return the tensors, once again, we're calling reduce mean on those tensors to be able to average the loss across microbatches. It is also possible to combine with data parallelism on PyTorch. So in this case, all you need to do is to pass DDP, which stands for distributed data parallel, to true while launching the training job. And the distributed model in this case actually handles the all reduce as well. So you don't need to explicitly make all reduce calls to implement data parallelism. Some example training logs. These are from actual training examples from TensorFlow and PyTorch. So as we said, during the first training step, the model parallel library actually does the automated partitioning. And then once that is done, it actually reports to you the statistics about the partition, things like which module is assigned to which device, how many parameters are assigned to each device, etc. And if you actually use SageMaker Studio, you have access to some additional statistics, things like the estimated amount of communication between devices and the number of operations on each device. Some example benchmarks that I'd like to share. The first one is from a training of GPT-2 XL, which is the largest variant with 1.5 billion parameters on TensorFlow with a few P3DN instances. So at the batch size that we're training, we actually run out of memory without the model parallel library. But once we integrate with the model parallel library, we can actually reliably train this model at the batch size that we choose. And similarly for PyTorch, we've actually tried running T5 with 3 billion parameters and scaled that up to 8 P3DN instances. And once again, we saw that it is not possible to fit this model without model parallelism, whereas we can reliably train this with the model parallel library. Some resources to get started with model parallelism today. Please check out the model parallel example notebooks and the Amazon SageMaker examples GitHub repository. So there are both examples for TensorFlow and PyTorch to help you get started. We're actually launching 2 separate distributed training capabilities today. In this session, you heard about model parallelism, and later you will also hear about data parallelism, so please feel free to check out that one too. Thank you for watching, and this is the end of the session.